In this adventure in algebra, we are going to discuss cyclic subgroups. So as an application of cyclic subgroups, we'll discuss something from the theory of music called the circle of fifths. So if you've played a musical instrument and you've studied musical theory, you might have heard of this concept, as it used to pop up in classical music. So the idea is that the normal musical scale is divided into 12 semitones. And the circle of fifths is given by starting at a note, like say C major, and when you go clockwise, you go up 7 semitones. So 7 semitones up from C major is G. And you keep going up 7 semitones. So above 7 semitones above G is D, and so on and so forth. And usually when you go up an octave, sometimes you drop down an octave, that's fine. But what you start to see happen is if you keep going up 7 semitones, after you do this 12 times, you circle back to the note you started with. And when you do this, you actually get all 12 semitones in this process. I mean, it's not the only way you could get all 12 semitones. The other sillier way would be to say start with C, then go to C sharp, then to D, then to E flat, then E, then F sharp, then G, and so on. But that sequence of notes sounds very, very boring, because it is clear that you're obviously just slightly increasing the tone just a little bit, whereas this one, it's a lot more dramatic. And so classical composers used to use the circle of fifths when writing their music, although you'll almost never see a piece that uses it exactly. They'd start with this and then they'd change some of the notes to make it a little more interesting. But the idea is that it turns out when you're adding 7 mod 12, you actually get all 12 numbers appearing. And we'll see that at the end of the end of the lecture videos, why that is. It's just interesting that that happens. And the application of cyclic subgroups you'll see is that there's essentially only 4 different types of approaches where you do this, where you keep playing and increasing the semitones by a constant amount and you get all 12 notes. You're either increasing by 1, decreasing by 1, increasing by 7, or decreasing by 7, and that's it. First, a definition. Let S be a subset of a group G. Then we're going to let angle brackets S denote the smallest subgroup H in G, so H is a subgroup of G, with the property that S is a subset of H. So remember, S itself is not a subgroup. It's just a subset for now. But we want the smallest subgroup containing S. And so we call this the subgroup generated by S. And it's a fact we'll prove later in one of the other videos that such a group always exists. But for now, we're going to focus on the case when S consists of just one element, in which case we will actually change notation and just rewrite it this way. So angle brackets element. It's the smallest group containing the element G. And that is the definition of a cyclic subgroup. A cyclic subgroup is any subgroup of the form angle brackets little g. So it's the smallest subgroup containing a given element. And the first theorem we're going to prove is that it consists of all powers of little g. So as a set, it's just powers of little g as n runs over all integers. And this proof is going to be using those properties of exponents that we proved at the end of the sequence of videos on groups. One thing I have to warn immediately is that it is not necessarily the case that this is an infinite set. Yes, it looks like that might be the case because it looks like there's infinitely many elements appearing here because there's infinitely many integers. But it could be the case that g squared is the identity, for instance. Like we've already seen with symmetries of an n-gon, one of the flips has order 2, so the cyclic subgroup generated by the flip only has 2 elements in it. But as simpler examples, if you work with z mod 6c, so this is congruence mod 6, and you look at the integer 1, the cyclic subgroup generated by 1, where you're looking at powers, so you've got 1, you've got 1 plus 1, which is 2, you've got 1 plus 1 plus 1, which is 3, 4, 5, and when you add 1 with itself 6 times, you get 0. So here we're working additively, and additively the group operation's addition, so we're just adding 1 to itself multiple times. See, it's not an infinite set, because if I add 1 to itself 100 times, I'm not going to get 100 mod 6. I'm not going to get 100, I'm going to get whatever the remainder is with 100 mod 6. What is it? 16 times 6 plus 4, so that's congruent to 4 mod 6. So I should be careful, I should be writing vertical bars here, because what I'm doing is I'm writing the vertical bar in place of the square brackets notation we were using before. The point is I'm doing addition, and whenever my number is greater than 6, I compute the remainder, and the remainder is my answer instead. And so there's only finitely many elements. Also worth pointing out that if I take the cyclic subgroup generated by 2, what do I get? I get 2. 2 plus 2 is 4. 2 plus 2 plus 2 is 6, which is 0. And you can see that any sum of 2's is going to be an even number, and even numbers mod 6 are going to be either 0, 2, or 4. And so the cyclic subgroup generated by 2 is this set. And so in this example, we have different cyclic subgroups, and they're not the same. Now let's look at the integers. Let's look at the same two numbers. The cyclic subgroup generated by 1 is every integer, because every positive integer can be achieved by adding 1 to itself enough times. So it's a certain power of n. Since we're going over all integers, negative powers corresponds to negation, so we also get negative 1, and subtracting 1 from itself enough times gives you all the negative numbers. So that's worth emphasizing, because we don't see that in these cases with the finite cyclic subgroups, but with this infinite one, you do actually need to pay attention that the negative powers are in here. What about the cyclic subgroup generated by 2? Well, 2 plus 2 is 4, 4 plus 2 is 6, 8, etc. You start to see that every even number can be written as a sum of 2's. So every even number, positive even integer, is in this set. And since you're closed under negation, all the negative even integers are in this set. So you get the set of even integers, which I'm going to denote by 2 times z, which is also not z. So we see the cyclic subgroup is always the smallest group containing the element you're interested in. Sometimes they're finite, sometimes they're infinite. And how big the group is depends on the element. So one last example, let's look at the complex numbers. Let's consider the cyclic subgroup generated by this element, square root of 2 over 2 plus square root of 2 over 2 times I. If you do the multiplication out and keep computing powers, if you square this element, you will get I. If you cube this element, so I should at least do that calculation. So first and last, the first terms minus the product of the last terms. And you see you do actually get 0 for the real part. What's the imaginary part? Well, you add the cross terms. And the cross terms give you 2 over 4 plus 2 over 4, which is 1. So you do get I. Now what happens if you cube instead? Well, the hard approach would be to make the mistake of cubing it. The easier approach would be to square it and then multiply it by itself. Why? Because we already just did that calculation. It's just I times this bit. And if you do that, you will get a negative real part. Now what about the fourth power? Where the fourth power is just the square of the second power. I squared is -1. And now the fifth power is just the fourth power times the original number, so it's just the negative. So everything else appearing here is just the negative of the first 4 elements. So we see these 8 things. This should cause some flashbacks from pre-calculus, because I'm really just looking at the cosine of pi over 4 plus the sine of pi over 4 times I. So these are just the xy coordinates of cosine sine of standard angles pi over 4, pi over 2, 3 pi over 4 pi, and so on and so forth, all the way till 2 pi. So this cyclic subgroup generated by this element is this set of 8 elements. They are the 8 vertices on a regular octagon. And we see that they are a finite subgroup. On the other hand, if you look at the cyclic subgroup generated by 1 in C, oh, I should have been careful. We're working with respect to multiplication, right? That's not true, is it? If you're only multiplying, you're only going to get 1. I guess a better example would have been to look at, say, 2. What are you going to get? You're going to get 2 to the n, where n is any power, according to my theorem, which means you're going to get 1, 2, 4, 8, 16, all powers of 2. But you're also going to have 1/2, 1/4, 1/8, and so on. So here the cyclic subgroup is infinite in size. So in this particular group, which to make it a group, I should have made sure it was clear we're talking about non-zero complex numbers, and that we're talking about multiplication. In this particular setup, you do have infinite cyclic subgroups and finite cyclic subgroups. So even within a specific group, you can get some interesting properties of cyclic subgroups.